Okay, so still on the associative network theories, we're going to talk about the spreading activation model that was offered by Collins and Loftus in 1975. This Loftus in this citation is Jeffrey Loftus. He was a professor at the University of Washington. Well, until very recently, he might even still be there. I think he's retired by now. We're also going to meet his former wife, Elizabeth Loftus, later when we talk about memory construction and stuff like that. So there's Jeffrey Loftus, who is big on these spreading activation models and things like that. And then there's Elizabeth Loftus, who's really famous for memory construction. So we'll talk about her later on. Okay. In the spreading activation model, concepts are connected by associations of varying strengths. Hey, this sounds familiar. Okay, so we're starting from the same basic premise. I found a different depiction of concepts. So this one's got fire engine as the concept. Activation of one node spreads to related nodes. So if you start to think about, let's say, fire engine, the most directly related things like ambulance and fire and house are going to become activated because you started thinking about fire engine. And then that activation is going to spread to other things that are related to fire and house and ambulance. But as you go farther away from the original activated node, you're going to lose strength. And so it'll ultimately peter out and you'll stop spreading at some point. So if you think fire engine and that causes you to think about red, you may be losing activation by the time you're getting out to roses. But you might not be. You might still have plenty of to be thinking about cherries, right? Like it could continue spreading out. But typically the way that we have a thought and it's focused and it's relevant is that the activation loses strength as it gets out, a couple of nodes deep. You stop thinking about, you stop spreading that activation so that you don't think about unrelated things. All right. So this we can't do, so I had to fast forward through that. So spreading activation, interconnected nodes, and you activate one node, it causes that to spread out to related nodes. In feature set theory, which was offered by Smith, Shobin, and Rips in 1974, the assumption is that there are features at each node. And just remember, the word node is sort of a substitute for synapse. They didn't really know at the time, so they were making these graphics that would represent what they thought was going on, and now we are pretty sure that it's synapses. All right, I found yet another version of a neural network. So here we have, it's not as hierarchical as the teachable language comprehender model, but you can still see that there are some kind of hierarchical qualities to this graphic, right? So we've got bird in the center. So we've got the overall concept bird. And then we've got some kinds of birds that are connected here. So we've got robin that's really strongly connected to the concept of bird. We've got ostrich that's more weakly connected to the concept of bird. And then we have these characteristics, can fly, has wings, has feathers, that are tied to bird. All three of those are tied to robin. Has feathers and has wings is tied to ostrich. So some of the details, some of the features can be connected to this related concepts, and some don't have to be, right? And then you can add additional ones: red-breasted for the robin, long legs and neck for the ostrich, right? So you've got these defining features at the top that really define that concept of bird, that really define those kinds of birds. Then on the bottom part are the characteristic features, things that are really characteristic of those instances. And so the fact that an ostrich is large and that a robin is small and that ostriches walk or run, whereas robins hop. These are characteristic features that really help to distinguish a robin from an ostrich or a robin from a sparrow or other, potential connections. So it's not as hierarchically structured as the teachable language comprehender had been. It's not as randomly structured as the spreading activation model. It's kind of a hybrid between the two, right? Where there's thought to be some structure, a reduction of redundancy, where you don't have the same concepts, same details, defining features repeated over and over again, or characteristic features repeated over and over again, but not quite hierarchical. The defining features would be central to the meaning of the concept, and the characteristic features would be strongly associated but not necessary for the concept. So in this example, to be a bird, you don't necessarily have to be small or walk, right? You don't have to have these characteristics. So the things that are characteristic features are strongly associated with individual members of the category. So you've got features at each node, like I just showed you, and then it's really a two-stage decision process in the feature set theory. First, you have to match the defining and the characteristic features to this instance. So let's say that you're seeing something out your window right now, and you're looking at it and saying, what is that? Well, first you would match the defining and characteristic features of the object out there. The more matches there are, the faster you can respond. Or if there's an absence of matches, the faster you can respond. If there are some matches and some no matches, like some things are there and some aren't, now you're going to have to go, okay, seriously, I've got to look at those defining characteristics and establish what I'm looking at out the window, right? So a good example of this probably isn't out your window, but it would be like a penguin. I don't know about you guys, but I was a little shocked when I found out that a penguin was a bird. Now this is a good example of a semantic memory. I don't remember when I learned this, but I was very shocked when I learned that a penguin was a bird, because it doesn't have any of the characteristics of bird as far as I'm concerned. It clearly doesn't have feathers, because look how smooth and shiny it is. Well, apparently those are wet feathers. So, I mean, honestly, I thought it had skin like an orca. I mean, it's colored like an orca. I thought it had skin like an orca. And then it doesn't fly, except it kind of looks like it's flying when it's swimming, doesn't it? But it doesn't fly. It doesn't make a nest. It doesn't get in trees. It doesn't sing. Like, it doesn't do anything that a bird's supposed to do. I guess it lays eggs. I'll give it that. Okay. Well, ultimately, to recognize that a penguin's a bird, you really do have to go back to those defining characteristics. Does it have feathers? I now know that those are actually feathers. So yes. Does it lay eggs? Yes. So if it has the defining characteristics, even if it's, a very odd example of the category, we have to ultimately recognize, okay, it matches the category. It actually has the defining characteristics. So we're going to respond a lot more quickly to those, according to this model, we're going to respond a lot more quickly to those instances that have, a lot of matches or absolutely no matches. If it doesn't match the concept at all, it has none of the defining or characteristic features, it's very easy to say, well, that's not a bird. But if it has some characteristics of the concept and some concepts are missing, now we have to really drill down and focus on those defining characteristics. So this is much more time consuming, because we have to sort through all the characteristics to isolate those that are defining and whether they're present or not. Like, in the absence of me ever being able to touch a penguin, which I can say in my entire life I've never gotten to touch a penguin. If we had to rely just on me seeing pictures of penguins wet, I still wouldn't know what that creature is. It doesn't look like it has feathers. Maybe it's a platypus type of creature that lays eggs, even though it's not really a bird, right? Like I would have been stumped. Very time consuming if you have to actually sort through and establish whether those characteristics are present or not. Luckily, someone else already did that, and I trust them that those are feathers and not skin. So you can imagine it takes a lot longer if it's now this would make a lot more sense if I had gotten to have feedback from you guys and we'd gotten to do something, but we didn't. So I'm going to go ahead and fast forward over that. And so we have our feature set theory. I got confused by my my little diagram of something that we didn't get to do. So feature set theory, we got this two-stage decision process. Let's go here. There we go. Okay. So we've got the features at each node. Okay. We already talked about that. It's a two-stage decision process. Okay, we already talked about that. There is a category distance effect in this model to account for the fact that it does take longer to establish, for example, that an ostrich is a bird than it does to establish that a robin is a bird. Typical instances share more features with the superordinate category of bird in this case, and so it allows for quicker identification. So in this model, the category distance effect is not occurring because you're having to literally travel up the categories like the teachable language comprehender implied. Instead, this model says how many features is shared with the superordinate category, right? So if you have a bird as your concept, and the defining features of a bird are has feathers, can fly, and has wings, well, robin has all three of those. Ostrich has two of those. So having more in common makes it easier, faster for you to identify a robin as a bird. So it has nothing to do with like actually physically moving up the hierarchy. It has more to do with how many characteristics are shared in common with the concept. All right, so let's talk a little bit about different types of concepts. I keep using the word concept, right? So what are concepts? Well, there are logical concepts, and a lot of times logical concepts are used for research purposes. So a logical concept is really a set of rules that you're going to learn for the purposes of this experiment. This is usually done so that we can watch people applying conceptual rules. Like, they have to have done it because this is all they know about the thing that they're doing. It's a really traditional strategy in concept identification studies to try and figure out how people are identifying things. So in the reception paradigm, the items are presented individually in random order, and the subjects are supposed to categorize the items. They have to use their memory to keep track of what items have already been categorized and make an attempt to be consistent. In the selection paradigm, all the items are going to be presented simultaneously. The subjects are going to categorize them. And in this strategy, it allows you to watch the subject's problem-solving technique as they try and figure out what category an item belongs in. Grouping strategies are based on attributes and rules, and the grouping strategy paradigm causes the subject to try to figure out which attributes and which rules really apply in this scenario. So let's see what I'm talking about here. All right, so you've got we'll just call it red. I don't know what color that is. So we'll say red square, red big circle, red small circle, white big circle, and white small circle. Okay, so in case you're not sure what you're looking at. Okay, so here I'm telling you that yes, the big square is an example of the concept, and you're trying to figure out what the concept is. So yes, the red square is an example of the concept. Yes, the big red circle is an example of the concept. No, the small red one is not an example of the concept. Yes, the big white one is an example of the concept. No, the small white one is not an example of the concept. So I'll bet you've figured out what the rule is for grouping right now. You probably have already figured it out. When we're doing these kinds of tasks, what we see is that people display conservative focusing, where at the beginning, all attributes are equally relevant because you don't know where you're going with this. So you're like, okay, there's shape, there's size, there's color. But as you go through the list and you're being told that this is an example and that's not, one feature at a time gets changed in the subject's mind. This is a really effective way of solving the problem, right? So hopefully you guys figured out that size was the correct. We were categorizing them by size, right? Not by color and not by shape. Focus gambling is when you risk varying two attributes at a time. And if you do it right, if you accidentally stumble on the right attributes, you learn really quickly. But if you make a mistake, you have to actually go back and start to display conservative focusing again to try and solve the problem. So a lot of times, people who start off focus gambling, they might do it and be right and be like, wow, I'm so smart, I figured that out the first time. But it was really luck. They didn't figure it out. They accidentally picked the right category. So for example, if you had done focus gambling at the very beginning, when I said yes to the big red square and yes to the big red circle, you might have thought color was the important thing, right? And then when I said no to the small one, then it clarified that that was wrong. But focus gambling might have made you say color right now. I'm going to say color. And then when you were wrong, then you'd have to go back and go, okay, wait a minute. How is the red one, the small red one, not an example? Now I have to go back and do conservative focusing. So conservative focusing tends to take a little bit longer because you're only, sort of altering one feature at a time, but it tends to be more often right. Focus gambling, you might be quick and sometimes right, but you might also be wrong and then have to go back. And then overall, you're slower. All right. That was logical concepts. And next would be natural concepts. I think this is a good time to take a little break. So let's come back and I'll start with natural concepts in the next segment.